Good evening, everyone. Am I audible?
Yes, sir.
So, before we begin today's class, is there any doubt that you would like to discuss or anything else?
Yes, sir. I have a doubt. Can I
Yes,
share my screen?
yes, you can.
Yes. Is it visible, sir?
Yes, it is visible.
Yes. So I recently did this simulation of a decanter, and sir has covered only two component in the lecture about decanter, and I added an additional component that is acetone with uh, xylene and water. Sir has only added xylene and water. I also added acetone for further study. But when I uh, specified that key component thing about decanter, and for more clarity, I did that. So in that case, sir has covered that when we specify key component a p-xylene, then we get p-xylene uh, less in upper stream and more in lower stream. Like data we get our p-silane is 0.233 in upper stream, and 999.766 in a lower stream when key component is p-xylene. And when key component is not chosen, then in upper we get p-xylene as 999.76 kg per hour, and in lower stream p-xylene is less. That means decanter is separating based on density, right?
Yes,
So I am getting some different data when I choose acetone as key component and p-xylene as a key component. Can I share my Excel sheet for a better comparison?
uh, you can share the input sheet of the decanter once.
Mm,
Go to blocks. Yes, selected.
okay.
So you have not selected key component over here.
Yes, I have not selected key component, but see, if I choose acetone as a key component, right, and then run this simulation and go to result summary, then I get uh, in lower stream uh, acetone this much, okay, 167.
Okay.
And when I choose uh, p-xylene as key component and then run and see, so I get same 167. Okay.
Actually, okay.
And one more thing I want to ask, that uh, specific gravity of uh, water is one. That means water is the heaviest,
Yes,
acetone is the lightest, and p xylene is
intermediate.
in between them, right?
Yes.
So when we never no don't choose any key component, then water should be maximum in the lower stream, and acetone must be maximum in upper stream. But when I choose no key component, then in lower stream, okay, so
Water is the highest. Then
water is the
acetone is intermediate.
acetone is intermediate, but p xylene must be intermediate na, because specific gravity of p xylene is in between.
Show me the density once again.
These are the densities.
Once again. And show me the result once.
Results are without choosing any key component.
Okay. Lowest stream.
Sorry,
Should we see the solubility also?
pardon me.
No, like Rohit was suggesting whether we should consider the solubility of this mixture as well.
Okay.
So, have you checked the solubility of these components, whether xylene, acetone, and water are they soluble or not? I know water and acetone are soluble with each other. Check the mass
Okay.
fraction once.
Uh,
Mass fraction is also the same way related to the mass flows. Actually, if you are using three components and
hmm.
if two of them are soluble with each other,
Hmm.
then naturally a solution will be formed.
Okay.
But if you are using two immiscible components with density difference, only then maximum separation can happen in a decanter.
Okay.
So water and acetone are soluble with each other.
Okay.
Okay, so that might be the reason why your result is getting affected. But if you are using like two components like p xylene and water,
Hmm.
check their solubility whether they're soluble or not. If they're insoluble,
Hmm.
then maximum separation is possible.
Okay.
Usually decanter is mainly used for separation based on density difference, right?
Right.
But if you are using components that are soluble with each other, then again you have to use some separator to get purified to enhance the purification of one stream compared to the other. So this
Okay.
lower stream that you are getting, so water and acetone is coming out in a mixture where water is 77% and acetone is 22%
Yes.
by weight fraction, right? So, and
Yes.
paraxylene is maximum at the top.
Yes.
Okay, so you are getting paraxylene of 2082 purity. So
Hmm.
now the lower stream has to be purified further to get the to get the to increase the purity of both the streams.
Okay. Okay. Got it.
So for that you need to add some separators. in the downstream.
Hmm. Yes. Thank you, sir.
Mm. So is there any more doubt from anyone else? Okay, fine. So let us start with today's class. So this will be the first question which we'll be handling today. So this is the question states that a mixture containing 58% acetone and 58% of water is to be separated into two streams. One that is enriched in acetone and the other enriched in water. The separation process consists of extraction of acetone from water to methyl isobutyl ketone, which preferentially dissolves acetone but is nearly immiscible with water. The overall goal of this problem is to separate the feed stream into two streams that have greater than 95% purity of water and acetone respectively.
Sir, sorry to disturb, but your screen is not shared.
Oh, sorry.
सर ये कौन से असाइनमेंट में क्वेश्चन?
Assignment in the sense?
ये क्वेश्चन जो आप बता रहे थे किधर है?
ये क्वेश्चन मैंने मतलब एक बुक से लिया हूँ.
अच्छा सर वो विजिबल नहीं है तो कुछ.
हाँ, वो मैं एक्चुअली स्क्रीन शेयर करना भूल गया था.
एक चीज़ और है राजदीप जी, मेरा सॉफ्टवेयर इंस्टॉल कर लिया, लाइसेंस एरर लिख के आता है बार बार.
आपका सॉफ्टवेयर मतलब काम तो कर रहा है ना अभी?
काम करते हैं पर स्क्रीन शेयर कर रहा था प्रणम ने, वैसा कुछ नहीं बन के आ रहा, सिर्फ ब्लैंक आता है.
अच्छा, आप एक बार दिखाएंगे? अभी आप स्क्रीन शेयर कर सकते हैं?
एंड में दिखाता हूँ मैं आपको, क्योंकि अभी फिर कनेक्टिविटी का इशू आ रहा है. मैं आपको एंड में दिखाता हूँ.
अच्छा, हाँ, ठीक है. So this is the question where there is a mixture containing 58% of acetone and 58% of water, and we have to separate it into two streams, which is one which is enriched in acetone and the other which is enriched in water. The separation process consists of extraction of acetone from water to methyl isobutyl ketone, which preferentially which preferentially dissolves acetone, but it is nearly immiscible with water. So what kind of like, if you see only this question, what is the chemical process that is coming to your mind?
Extraction.
सेपरेशन.
Extracted.
Okay.
Extraction.
Huh. So I hope you know the basics of extraction, where the separation takes place based on the solubility. And this is an example of liquid-liquid extraction, where we are using another liquid to separate two components that are miscible with each other using an solvent that is miscible with one, whereas it is immiscible with the other. Now, the overall goal of this problem is to separate the feed stream, that is the acetone and water stream, such that we get 95% purity of water and acetone respectively. The flow rate of acetone water mixture is 100 kg per hour, and the flow rate of MIBK, that is methyl isobutyl ketone, is 100 kg per hour. Okay. So I would like all of you to start the simulation, like uh, like complete the input of components first, and then we are going to go ahead.
अभी राजदीप जी मेरा ये खुला है, मैं आपको स्क्रीन शेयर करूँ? दिस इज फाइन. जो अभी मेरा आया है वो मैं आपको दिखा सकता है कोई?
अच्छा, दिखाइए. For method name, try using NRTL. So it is working.
Okay, sir. Thank you.
First, using the method assistant, tell me what are the different methods that we can choose. I hope you all remember the method assistant that I had shown in the last class, where depending upon the condition of the process, the Aspen suggests us the different property methods that we can choose from the list of thermodynamic properties that are listed in Aspen.
सर एक बार फिर रिपीट कर देगा तो बेटर है सर, लास्ट क्लास नहीं कर पाते अटेंड प्लीज.
Okay, so except for Abhinav, I hope the other people did who have attended the last class know how to check the method assistant. And I think in the last class there was some question regarding what will happen if we use different methods for a problem. So I'm going to start with new simulation. Let me save this file. So what are the components that we have to add? We have to add acetone. Next we have to add water. And the third component is methyl isobutyl ketone. Let us rename this as MIBK. Now we have set up the components. Now we are going to click on next. Now let us choose NRTL. Okay, so method assistant, when we don't know which method to use, so we can select this method assistant tab over here. So what method assistant does is it helps us to pick up a thermodynamic property method for the process that we are about to design. So here it is asking us specify the component type or specify the process type. So let us go ahead with the component type. So what is our system? Chemical system, hydrocarbon system, special system, or refrigerants. So we have a chemical system. Since it is not entirely hydrocarbon, we have hydrocarbon and water together. So we are going to select chemical system. So is the system at high pressure? No, it is not. So over here we have this activity coefficient model of NRTL, Wilson, Uniquac or Unifac. Okay, so let us see what with this NRTL property method. So let us click on next. So once you have selected NRTL, you can see that from these data sources, the interaction parameters of acetone water, acetone MIBK and water MIBK have been updated from, and it has been retrieved from the Aspen database. Now once this is done, we are going to click on next and we are going to run the property analysis or setup. So here this part of our simulation is successful. Now let us go to the simulation page. So now we have to perform extraction, right? So what do we have to do?
First, we need to mix these two liquids, and then we need a separator to separate them.
Okay, so first is a mixer, right? So here we have mixer. We are going to place it over here. Let us rename this block as mix 1. Now we have the material stream. So I hope you know what this red arrow and the blue arrow indicates. So red arrows are the streams that you have to specify. That is, they are not optional streams. In order to perform the simulation using this block, you have to specify the red arrows that you are sending inside this block. So over here it is said that feed, since it is colored red, it is said required one or more if mixing material streams. And over here we have this product stream, that is, it is required. And then this is water decanter free or dirty stream, that is, if you want to decant water, then you can use this stream. Now this is optional, since it is not in red, it is colored blue. So here, how many streams we have to enter? There will be two streams. One is the solution stream, that is of water and acetone. Okay, so you can also align these arrows by clicking like this over here and then select align block. We can enter another stream. Now if you notice, once I have given one stream as input, the second arrow, which was red initially, has become blue. Like, you can or cannot enter another stream for this block, but we need the second stream because we need to give the solvent for extraction. So for this, you can also align like that and can do it like this. So
सर एक बारी मैं अपना स्क्रीन शेयर करूँ, ये मैं प्रॉपर्टीज डाल रहा हूँ, वो एसीटोन वगैरह सब मिल नहीं रहा सर, एक बारी आप बताएंगे कहाँ गलती कर रहा हूँ?
acetone, actually
वाटर
can
एसीटोन भी नहीं मिल रहा, एक बारी आप हेल्प करेंगे तो देख सकते हैं.
just give me 1 second.
ठीक है सर, थैंक यू.
And this is the product stream over here. Okay, so this becomes our H2 acetone stream, and this stream is our MIBK, and this stream becomes the mixture. Fine. So I am showing how to select the component one more time. So you are coming to the new simulation. So there are two ways of adding a component. So let's say if you want to add water, what you can do is you need to write water over here and then press tab. So water gets added. Another way is you can click find over here. Then you have to go to equals and then you have to write the component name. So here I'm writing acetone. And when I'm selecting find now, so here you will get acetone like this. Similarly, for MIBK, you have to go to find, write equals, and then you have to write methyl isobutyl ketone, and then select find now. So methyl isobutyl ketone will come from the database. You need to select it like this. So I hope it is clear.
Yes, sir. Now it's clear, sir. Thank you.
Now, once we have done this, our next step is to specify the feed streams. So once we click next over here, it is going to take us to the input sheet. So first is our water acetone mixture. So what is the temperature at which we can say that the water and acetone is mixed? Let us just say that we are doing it at ambient temperature, 25. Let the pressure be 1 atmosphere. The flow rate is given as 100 kg per hour. And they are equimolar or they are equal mass percentage. So we are going to select mass fraction. So acetone is 0.5 and water is also 0.5. Now once all the inputs are complete, we are going to get a blue tick over here. Next is MIBK. So MIBK also, let us assume it is at 25 degrees Celsius. The pressure is 1 atmosphere and the flow rate basis is mass. We are giving 100 kg per hour of MIBK. And the mass fraction for MIBK, this is pure MIBK, so it is 1. Okay. Now once we have given the input of the two streams, Aspen is going to calculate the result of the output stream. And it is telling here that the required input is complete. Mixing block is one block where no extra specifications of the operating conditions of the block are required. Or if you open over here, most of these are filled in. You can see it is filled by Aspen. So you don't need to fill the blocks. However, if you want your stream to be at a particular condition, you can specify. So since I'm mixing it in an atmospheric pressure, I want it to be in atmospheric pressure. So I have clicked one over here. Similarly, if you want the temperature to be the same, so that no heating process takes place due to the mixing, so you can specify that as well. The temperature estimate is also 25 degrees centigrade. I have estimated over here. Now the required input is complete. We are going to click on next.
Hello,
Yes.
sir. Don't we need to change the valid phases
Why?
from liquid? Yeah, is there no need? Because we have all in liquid phases, right?
You need to think about this as in you're using a mixer block, right? So suppose you are mixing two streams that are in liquid at atmospheric condition and ambient temperature. So if there is no heat involved, naturally no phase change will also be involved over here.
Yes.
So you can change over here as liquid only. That won't do any harm. You can do that also.
Okay. I just wanted to ask: is it really necessary, or
Okay.
we can
No,
just
if you want to specify Aspen that you have to, then you have to fill in these inputs.
okay. Thank you.
So it is telling that the required input is complete. We are going to click on next. And now it is asking us whether we want to run the simulation or not. So we are going to click on OK. So here the simulation is complete. Now this is how a particular like process stream process looks like. Now over here, what you can do is you can see the temperature of the streams. You can see that after mixing, the temperature has got lowered over here. Okay. Now if we want to see the pressure is the same. Now why did this happen? Can anyone tell me? Why did the temperature reduce? Can anybody tell me why did the temperature decrease over here? So actually, acetone, water, and MIBK, if three components, if the volatilities of the three components are studied, then water is the most volatile among the three components. Acetone is highest, and MIBK is intermediate. Whenever we mix components that have differences in volatility, what will happen even if we specify this stream to have the same temperature, some temperature drop is going to happen because a part of this acetone does get evaporated. So due to this, what will happen? A little bit of temperature drop does take place. So that is why this temperature difference is seen over here. Okay. And also the reason is if there is volatile components in a mixture and we are subjecting it to atmospheric conditions, so naturally the ones which are more volatile are bound to evaporate from the mixture. So that is why this temperature drop is seen.
So it means if it is evaporating, there means there is some loss of it.
Not actually loss from the system, but that is being accounted by the property that is there inside this particular method. It's not like we are losing out, but if we consider this stream over here, then due to the mixing of these volatile components together, there will be a little bit of uh, temperature difference that will be caused due to this mixing. Like just like reaction, mixing is also a process that can be endothermic or exothermic. Okay, so few mixtures when we are mixing them, like some liquid mixtures, they do undergo endothermic reactions or processes. That is, they absorb heat when they are mixed. Like one of this example is this mixture over here. And the main reason for this endothermic mixing is because of this uh, differences in the volatility of these components.
See, this I have practically experienced while we mix methanol with steam for generation
Yes.
of hydrogen.
Yes.
This we have seen the temperature drops in the
Yes.
system. Yes.
So now this simulation is complete. Now we have to see the composition of this mixture. So what we can do is we can go to this result summary over here. We can go to the stream. Now our resulting stream is trimix. So what was our objective? Our objective was to get 0.95 purity. But you can see that the purity is far below from 0.95. Another thing is that when we go to the results of this section and we can go to the balance over here, so here we get the enthalpy balance and the mass balance and the mole balance. Okay, so I just want like one or two of you, I have done it with NRTL. I want one of you to do it with Wilson and the other one with Uniquac. We had three properties that were given to us for that is suitable for this type of processes. I want you to do it and just report this enthalpy change. That is the value of this enthalpy that we are getting. That is the input enthalpy and the output enthalpy, or just this table. I want all of you to generate and just report me the values using the two different property methods. So do it on your own. I'm giving 5 minutes of time for this. I'm writing the question in the message box over here. Use Wilson model and Uniquac.
Excuse me, sir.
Yes.
I am facing problem in installing the software.
What problem are you facing?
Like it's showing that failed to initialize Aspen properties in enterprise database. Uh, we were not able to load any of the database. Please use database tester or database manager to diagnose the problem. You may need to register or record restore database. Aspen plus must be closed. This type. Like
Where did you start? Did you ever like run the software before this? As in, have you
no.
installed it properly? Then I would suggest you to uninstall the install software and carry out the process once again. And try to
Yeah.
download the entire software from a different link that you have taken from.
Okay. So I have tried one more time, like downloaded from different link, then installed. Then I faced the same problem.
Okay. From which link are you downloading the software? Are you downloading the software from the G drive or the NPTEL link that was given to you? Hello?
Hello. Firstly, I downloaded it from Drive link and then from NPTEL link. Second.
Drive link as in G drive.
Yeah, G Google Drive.
Okay. This usually happens when all the databases are not properly given in the files that you have downloaded. It is telling that it is
Uh,
missing.
I pro- I proceeded according to the PDF in the for installation provided.
Okay. Try to mail this problem to the NPTEL people once, because this problem usually occurs when all the database or the all the data like this database files are not properly present in with given with the installation folder. Or it's just share your
Yeah.
screen once this problem is over that we have discussed it. Okay,
Okay.
then I'll see it. And
So where I have to share the problem?
there will be an NPTEL this group is there, no, where we from where we get these mails that we have online interaction class.
Yeah, discussion forum.
Yes, yes. So try to give it over
Okay.
there.
I have posted it there. The reply was that solve it in the solving problem session.
They have set in the solving problem session.
Yeah, I have taken the screenshot of the problem and then posted on there.
Hmm.
Then the reply was that use other alternatives till problem solving session.
Okay, okay. Then just give me a bit of time and I'll look into it. So this was for Uniquack and last is for Wilson. So in Wilson, there is one problem. You can see that acetone water and acetone MIBK is given, but water and MIBK is not, the interaction parameters are not there. So
रिपीट करना सर, रिपीट करने कहाँ से है?
like when we selected Wilson property method, in the previous two property methods, NRTL and UNIQUAC, we got the interaction parameters like for acetone water, acetone MIBK, but and then MIBK and water interaction parameters are also needed. In NRTL and UNIQUAC property methods, these interaction parameters are retrieved from this database. But when we have selecting Wilson property method, the interaction parameters are not shown.
So ये विल्सन एक बार फिर से सिलेक्ट करना, अगर कहाँ से करा विल्सन एनालिसिस में जाके.
So we have come to the methods. I'm going to show you for UNIQUAC. UNIQUAC. So over here it is telling input is changed. Okay. And I'm clicking on next. Oh, sorry. So in UNIQUAC, you can see that the 3 pairs of interaction parameters are given, auto-updated. That is retrieved from this database. But if you go to the Wilson, only 2 are there, but the third interaction is not there. So what should we do in this case?
Estimate using Unicode.
Yes, we can do that. So we are going to click on estimate using UNIQUAC. We are going to click on next. So first, we have to change it to Wilson first. So let us see our Wilson. So here water and MIBK, it is being calculated from RPCES. Okay. Now going to the simulation. Now we are going to select reset over here. Now we are going to click on next. So over here, let us go to results and we will change it to June per second. So this is the for Wilson. So the I did check the results that you have given over here. The results that you have got is 88964. It might be in calorie per second. Yes, the result that you have reported is correct only. So this is for Wilson. Now the question is, 3 of the property methods are giving correct results only, but there are changes in the enthalpy values every time we are changing this property method. So the question that I have is, like, out of these 3, which property method should we choose? We have done this type of problem in the last class. So try to think and let's just come up with some way as to determine out of these 3 methods, that is NRTL, UNIQUAC and Wilson, how to determine which method or which property method should we use.
Maybe the one with the maximum enthalpy.
Why?
Just to be safe, like how we do in the activation energy in CRE, just like that, just to be safe, we use the one with the maximum enthalpy requirement.
But activation energy is directly
Uh,
activation energy is mainly there so that it is like a barrier, right? We need to overcome that barrier for the reaction to take place.
yes, I am just guessing.
Okay. So over here, you can see that the enthalpies are different, like every time we change the property method, right? Now the question is, like last class, somebody had asked like how to determine which property method should we use. In the last class, we had also done another thing. One was we had done regression using experimental data from NIST database. Okay. So the people who had attended the last class, like I would want three of you to do the regression of the Uniquac, Wilson, and NRTL model using the experimental data of water and MIBK that you will get from the NIST database. So if you want, you can refer to the previous class videos and tell me the RMSC values, that is the root mean square error value that you are getting from the regression of these three databases or from these three property methods. I'm going to do it from my end also, but I would like all of you to try it on your own. So as to like so as questions such as which property method is best suitable for a particular process, this is how we actually choose a particular property method when we are in confusion, because Aspen has given us multiple options to choose from a property method, and none of these property methods are actually wrong. You can see that the difference of these property methods, the values that they are giving, they are almost correct, and there is perfect mass balance and energy balance across the block over here. That is, it is of the order of 10 to the power minus 16, which is highly negligible. But even then, for the sake of accuracy, if we want to determine which property method we have to choose, in that case, what we should do, I just want to discuss on that top part. We usually do this with the help of regression. So I am going to show it from my end also, but you also try to apply yourself and find out through regression which property method is the best. And the best way to do it is to calculate the RMSC values from the experiment between the experimental data and the regression that you will perform in Aspen. So try it on your own.
सर एक बार फिर से रिपीट करना सर.
So last class we had actually done the regression, how to do regression using experimental data from NIST database. So we have seen in this class that there are three property methods: NRTL, Uniquac, and Wilson. These three property
ये तो
methods were
क्लियर था,
suggested by
ये तो
Aspen.
क्लियर थी.
Huh?
ठीक है सर, बताइए सर आगे.
So you can see that the relative difference between in when these property methods are being used, the difference is not there. Like they are almost of the same value. Hardly there are any changes. Then when we are getting this equally competitive three thermodynamic property methods, which one we should choose? Because we can't choose three property methods for one process, right? So how to determine which of it is out of these three, which one is the best? That is what I'm asking. So how to do that? So for that, I'm suggesting you need to do regression analysis using the experimental data that is available in the NIST database. I had shown how to do the regression analysis in the previous class, so I'm just asking you to do that. Like all of you are there, pick up one property method. Let's say you pick up NRTL property method and do the regression analysis for the NRTL property method of water and MIBK system, and just report the RMSC value, that is the root mean square error value. Is it understood?
Yes, sir, but last class I was not there, no? So I was not
So you
aware
can
of this.
check the video, it's there in YouTube.
Okay, sir. Sure, sure, sure.
So for regression, we are going to go to the NIST-TD database. What we have to do, we have to find out the binary interaction of these. So first, let us see which components have a good database. So before doing regression, we also need to determine what what are all the different uh, components that do have a good database for us to perform regression. So let us first check
सर ये
acid.
विंडो कहाँ से पॉपअप कहाँ से आया सर? ये पॉपअप कहाँ से आया?
So it has come from here, this NIST. Go to properties
ओके सर, ओके.
and then go to NIST over
NIST.
here.
ओके सर, ओके.
So, and from here you are going to select binary mixture. So here we have, first let us check with acetone and let us check with MIBK. So now what we are going to do is we are going to do retrieve data. So it is telling that NISTTD is retrieving binary experimental data. Now these are the different data sets that have been retrieved for acetone and MIBK mixture. So to check which one is like if it is good or not, we do the consistency test. So we are going to run the consistency test. So you can see that for the binary, it is telling that all the tests are failed for this mixture over here, acetone and MIBK. And the overall data quality is very low, that is 0.167. So let us delete this. Again, let us go to NIST. Now again for a binary mixture, we have to select. Now what we are going to select, we are going to select for MIBK and water. So here it is water and this is MIBK. We are going to retrieve data. There are multiple datas have been obtained. Let us go to consistency test. Let us again run the consistency test. We are going to run OK. So here they are not telling any particular, but the overall data quality is still low over here, which shows that this data quality is also not good. So now the last pair is left. Then again we have to select binary mixture. Now let us select for acetone and water. It has retrieved data. Data has been retrieved. Let us go to consistency test. Let us run the consistency test. So the consistency test of all the values are there. So you can see there are few results are there that have passed. So out of here we need to select the one that has the highest overall data quality. You can see this particular data quality over here. So this particular data quality, that is of a study that is reported in 1984, that has a highest data quality of 1. And you can see that it has passed almost all the tests. So we can use this data over here for our regression. Okay, so this is our binary VLE. That is, this name is binary VLE 104. So come to the experimental data. So here we have binary VLE 104, and we are going to save this data. We are going to click on OK. Okay. So this data is saved. Okay. Now we have to perform the regression. So for that, what we have to do?
So can you tell once how to save this data?
We got the data like
You have, yeah. Once
then
you
you
finalize with the percentage, no? After that, how to save that data?
can you share your screen? I'll show it over there. I have done it from my end. If I do it again, this entire thing I have to go back.
So I'm operating on a different laptop. That's fine.
So join from that laptop. It won't be a problem. I just because if I try
Okay,
to
I identify which has a highest number of. I mean, one was there which was
yes,
passed,
yes, yes, yes.
and on the left side, I have sorted out that number.
Yes, yes.
Okay.
You have to identify that particular data
Yeah.
number, that is VLE 104, which we
Right.
have.
And after that,
Over there, go to the experimental results.
okay,
Then there is 104. Select it and then select save data.
okay, fine, sir.
Were you able to do it?
Thank you. Yes, sir.
Now, can anyone tell me how to do the regression? So first we have to select this. We have to select new dr1. Now the method that we are going to do is we are going to do three methods, right? We are going to do it with Wilson, then NRTL and Uniquac. So first let us do it with Wilson. So it is asking for a database. We have one database over here. Now going to parameters. So we have to fill the parameters over here, right? So do you remember how to enter the parameters over here? So first is our binary parameter. So the name is, we are doing it with Wilson. Element is going to be 1. Component is acetone. And group, it is water. Then again there will be binary parameter. We are actually trying to fill up how it is being shown over here. Okay. This is Wilson. Acetone. MIBK. So this is done. Click on next. So run data regression cases.
तो ये एलिमेंट 112 क्या मतलब है इसका?
So it is the element numbers. There are 3 elements like 1, 2, 3.
तो 1 2 3 क्यों नहीं नंबरिंग करी सबने? 112 को किया.
It is like it is the element, like what are the interactions that we are seeing, like with respect to the first component, that is acetone. So that is why 1, 1 and 2, that is acetone. With respect to acetone, 2 comparisons are there, and then with respect to MIBK, that is element 2, that is 1 comparison is there.
ये कोई फिर रिपीट कर दीजिए.
So here the Wilson parameters are updated. Just give me 1 second, I'm telling you. So if we look at the sum of squares, the mean square is 22.0852 for Wilson. Let us just write this. So in parameters, what we are doing is we are selecting the element over the binary interaction parameters. They are usually defined like in respect to which element are you going to calculate the binary interaction parameters, right? So when I am selecting 1, over here I have written acetone as 1. So with respect to acetone, what is the interaction of water? So over here, water is my second element. So I'm selecting with respect to water, what is the interaction of MIBK. So that is why I have written
Okay.
1, 1 and 2. Okay. So try to find out the root mean square error for the other 2 methods. That is for NRTL and Uniquac. So over here, what you have to do is just now you need to change it to NRTL. Okay. The parameters, they have, you see that now they have changed. Few are fixed. One we can find it by regression. Now we are going to click on run. Let's go to the results. Here you can see the RMSC is 7.47281. This is for NRTL. We can update the parameters or we can let it be. It's not a problem since we are not focusing on updating parameters as of now. And the last is our unique VAC. So this has a residual mean error of 4.05. So which one should we choose? What do you think? Like which one should we choose? You can unmute and tell me.
Unique work,
Why?
because it has a minimum RMSE values. That's
Yes,
why.
yes. So whenever there is a doubt, when three property methods are there and you are not able to understand which one you should choose, then in that case, and it is very important for you to determine the thermodynamic property that you should choose. In that case, you should always perform this regression analysis and find out which property method gives you the least root mean square error with the experimental data. Once you have found that, then go with that property method for your process or for your simulation. So over here, what we are going to do is we are going to just update this to unique VAC since it has given the least RMSC values. So we are going to reset. We are going to click on next. Okay, we don't want regression to be done anymore. So let's say if you have done regression over here and you don't want to perform regression, what you have to do is you just to click and just delete. So this regression tab will be gone. So you just click on next. Delete this data as well. Enter the sets to be regressed. So we had already selected this regression tab over here. That is why it was asking for regression data. So when I am moving it to this analysis part, so you can see the change run mode to property analysis. So naturally the regression is not, data is not required. So it is telling that the required properties input is complete. So we are going to click on next and we are going to click on OK. So the results are available. So now let us go to the simulation. Since we have changed the this thermodynamic property method a couple of times, let us just perform the simulation one more time. So now this is done. Now coming to the second part of this question, like over here, the purity that we have got is not 95%. So what do we have to do now? What do we know about this stream? As in, there are volatile components, and what we usually do when we have volatile components. Anyone?
Distillation.
Distillation. Is there anything simpler that we can use? First, they need to be separated by density difference. But density and volatility are two different properties. They are not the same.
Evaporation sir.
Evaporation.
हाँ, थोड़ा सा
Anything else you are thinking at the right track?
थोड़ा सा हीट करके उसको एक्सट्रैक्ट कर लिया जाए.
So there is another process for it. Can you recall a simpler process like distillation, but not exactly distillation?
Flashing.
Yes. So the next, what we are going to do is we are going to add flash drum. So there are different types of flash drums. So flash 2, it actually gives us 2 outlet flash. What we are going to do is we are going to do flash 3, where we can have 3 streams coming out of one flash drum. So let me select this flash 3 and put it over here. Let me reduce the size of this. Now what we are going to do is we are going to connect this trimix stream into the flash drum. Okay. This is done. Now what we have to do is we have to complete this flash drum material streams. So there are 3. That is, one is the vapor. This is the bottoms, and this is a liquid that we can draw from here. So this, let us rename it as FL1 vapor. This is FL1 water, and this is FL1 MIB. I had told you that acetone is most volatile, MIBK is intermediate, and water is the least volatile component in this mixture. So naturally we are going to have a higher percentage of water in the bottom stream with acetone vapors, and the intermediate stream with a higher component of MIBK.
Sir, excuse me.
Yes.
Sir, I have a doubt. While connecting this trimix stream to this flash separator, in between them, one more block is coming, sir. How to connect this one trimix to flash separator?
Okay, wait. I have deleted this stream. Okay. Now this is the trimix stream. I'm not connecting it. I'm just this much we are done in the previous simulation.
Right.
Any doubt?
No. Correct.
Now just select this stream, right click, reconnect destination. Click this arrow and then just take a left click. It will be done. Were you able to do it?
Yes, sir. Yes, I have done. Yes.
Okay. Now there are two ways how we can operate a flash drum. One is one is isothermal and one is isobaric. So in isobaric flashing, what happens is we do not change the pressure of the flash drum, but we change the temperature. And in isothermal flashing, what happens is we do not change the temperature of the flash drum, but we decrease the pressure. So in this case, what we are going to do is we are going to perform isobaric flashing. That is, we are going to keep the pressure same, but we are going to change the temperature. What do we have to do? So if I no, it is not there. So if you remember, this temperature over here was approximately 19 to 20 degrees Celsius. So what should be the temperature of the flash drum for the separation?
It will be less, I think, sir.
Less. If you keep the pressure same and if you keep the temperature less than the temperature that
No,
is...
no, you have to increase the temperature. Increase the temperature.
Right. So going to this flash drum over here, we have the temperature. Let us say the temperature is 50 degrees Celsius. The pressure we are keeping the same as 1 atmosphere. So once we have specified the temperature and pressure of the flash drum, you can see that the input is changed. That is, no further inputs are required. Now we can run the flash drum. For the next problem that we are going to do, try to keep this in mind. There are different input options that we can give in a flash drum. Duty and vapor fraction. Okay, just keep in mind this point that I have just mentioned now. Now we are going to reset this. Now we are going to run the simulation. So results are available. Now we want to see the composition. So let us check this vapor composition over here.
तुमचा किती वेळ आहे किती वेळ सांगा ना मग मी भाजी बनवायला जाईल तशी भाजी बनव की वेळ आहे अर्धा तास लागेल
There is no vapor that is being formed. Okay, let us check the mass fractions. So these two, so vaporization, vaporization will not happen also because the temperature that we have given is relatively low. So Over here, acetone, water is 81 MIBK. And over here, MIBK is more, that is of this stream, MIBK is more. That is for the stream that we are drawing out. MIBK is more, water is less, and there is a mixture of acetone. So when are we going to get vapors from here? In order to get vapor, we need to increase this temperature above the bubble point of this mixture. Bubble point of pure water is 100. So if we keep this as 100 degrees Celsius, we are going to get vapor stream. Yes. Let us see. Now you can see that we are getting vapor streams over here. Previously, we were not getting any vapor stream. However, let us keep this as 50 degrees Celsius only, since getting vapor is not our objective as of this moment. Now our point was to improve the purity of water, right? So over here, that is the bottom stream that is coming out from the flash drum. You can see that MIBK is low, but acetone and water mixture is around 20% is acetone and water is 80%, around 80%. So to improve this, what we can do next, we can do one thing. We can just repeat this entire process one more time. That is, I'm going to add another mixer over here. Let me rename this as mix 2. Add this stream over here. Now for redoing this, we have to add another MIBK stream. So I'm going to add an extra MIBK as a solvent. Let me rename this as MIBK1 and this as MIBK2. So the product of this stream is going to go inside another flash separator. I am actually replicating this process over here again, so as to improve the purity of water. So reconnect. So this is reconnected. Align blocks. This is try mix 2. This is mix 2. This is FL2. Over here also we are going to have 3 streams. This is FL2 vapor. This is FL2 MIBK. And this is FL2H2O. FL2H2O. Fl2 MIBK. And this is Fl2 vapor. Okay. For now, we have added one block and another stream. So two inputs are required. So over here, MIBK2, which we have added new. So this MIBK2, which we have added new. So let us go over here. Let us specify the streams. Let us not change the input specifications that we have kept previously, 25 degrees Celsius, 1 atmospheric pressure. The mass flow rate is going to be 100 kg per hour, and MIBK is 1 mass fraction, that is pure MIBK. Done. Our next part is to input the specification of flash 2. We are going to keep the temperature same, that is 50 degrees Celsius, and the atmospheric pressure is 1 atmosphere. Okay. Now what we can do is we are going to reset the stream. Okay. Now we are going to click on next.
नागपुराच्या आगर कशाला वापस आला तुम्ही
So here you can see this stream over here. If we check the mass fractions, you can see that it is still not 95%, but high purity of water is now available. It is around 94%. So for achieving 95%, there are two ways what we can do. Okay, these we will cover in the upcoming classes. One is sensitivity analysis and the other is design specs. So let us do using the design spec. What a design spec? Design spec is an inbuilt operation that is provided by MATLAB provided in Aspen, in which we can like specify one design spec of this entire process. Now, what is a design spec? Design spec can be anything. I'm giving a small example. When we are setting the flow rate of streams, we are actually specifying this is one design spec of our process. That is the flow rate of this MIBK. The flow rate of these two feed streams, this is one design spec. The operating condition of the flash drum, this is also a design spec. Okay, if you remember, this one was the first separation process that we had performed, and this is the second MIBK that we are sending in. So I would like to change this design spec so as to improve the purity of water that we are getting from here. Okay, so how to do it? You have to come to this flow sheeting options. Over here you have design specs. You have to select this. Click on new. So one design spec ID will be created. Now click on OK. Now over here it is going to ask the variables. So what are we going to define? We are going to define the weight fraction of water. So I'm going to write it as WFRAC. I'm going to click on OK. What is this variable? This is a stream variable. Sorry, this is a mass fraction that we are going to calculate. So here it is written mass fraction. You select mass fraction. What is the stream? The stream is Fl2H2O. That is the last stream that is coming out from our process. That is this stream. Okay. So I've selected Fl2H2O. What is the component? The component is water. This is defined. Now we are going to specify. So W frac, what is the target that we want to achieve? We want to achieve the purity of 0.95. And what is the tolerance? The tolerance, let's say we want a 10 to the power minus 3 tolerance. Now what we are going to vary? What we are going to vary? We are going to vary the stream flow. The stream flow of what? The stream flow of this MIBK that we are adding in the mixture 2. So now we are going to select the stream variable. What is the stream? The stream is MIBK2. What is the variable? Mass flow. Okay. And the mass flow we have mentioned, you have to be very careful as to the units that you are specifying over here. In the input of our MIBK over here, if you remember this MIBK input, we had set it in kg per hour. So here also you have to set the unit in kg per hour. Now we had 50, which we already had 100 specified. Now we are going to increase it to, let's say, 200. And let's say the step size is not required. Aspen is going to do it on its own. Now it is telling input is changed. Now we're going to click on next. And we're going to run the simulation. So remember, we had already got 0.94 purity. Now if you come to results, you can see that initially our value was 100. We had a weight fraction of 0.94. Now the final value is 136.46 and the purity is 0.95. So if we use this value over here, and we reset the simulation, now if you check the mass fraction of water, you can see that 95 purity is opted. Is there any doubt?
तो इसमें हम इक्विपमेंट्स के स्पेसिफिकेशन भी आ जाते हैं क्या इसमें?
As of now, we are only performing steady state simulations. If you want to do dynamic simulations, in that case, we can get the specification of the equipments as well, as in the length.
वो आगे करेंगे हम?
Yes, we are going to do it. So is there any doubt of this particular problem?
Yes, sir. I have one doubt, sir.
Yes.
Sir, from flash 1 drum to the flash 2 drum, there will be some pressure drop. And we are maintaining the same pressure.
Actually, over here, we are assuming that pressure drop is not there, okay? In real-time scenarios, pressure drop will be there since we are moving the streams from one equipment to the other equipment, firstly. Secondly, we can use a pump for delivery. In that case, some pump power will be involved in between. Or else, if we don't want to use the pump, then we have to operate this at a higher pressure than this. This is a very simple simulation with the assumption that no pressure drop is taking place in the transfer of materials from the flash 1 drum to flash 2 drum.
Okay.
Sir, can we fine tune MIBK1 to change the purity of water in FL1H2?
Sorry?
Here we change MIBK2 flow rate to increase the purity of water in FL2.
Yes, you can try it. You can try and see what happens.
Okay.
You can try this also. You can try
Yes,
this,
sir.
the operating temperature and pressure of these equipments also, and see.
Oh, yes. Okay.
I have just given you one example.
Yes, thank you. Understood.
So let us go to the next question. So this is one problem placed on flash drum. Okay. So I won't be covering all the questions. I will be uploading it in the Google Drive also. So try to do the questions that I'm not solving in the class. This is a simple question which you can do. I'm explaining this question. So there is a hydrocarbon mixture. Okay. Now, you know the volatilities of the mixture will depend on the molecular weight. So naturally, C4, IC4 and NC4, which one is the more volatile out of these two? NC4 is the less volatile compared to IC4. because IC4 there is isomerization, this one is iso due to the molecular structure. This one is more volatile compared to NC4. Okay, so depending on the volatility, flashing will happen, and the property method is given cis of 0. The temperature and pressure of the flash 2 is also given. So try to simulate this problem and see the results that you are getting. Okay, this problem you can practice on your own. This is not much of a difficult problem. Now this problem we are going to do, I'm going to give you 2 minutes of time. Try to tell me how we can compute the dew point temperature at 1.5 bar of hydrocarbon mixture using Arkershoff property method. These are the components. The temperature and pressure of the inlet mixture is given. That is 25 degrees centigrade and 5 bar, and the flow rate is 120 kilomole per hour. We are going to use a flash drum, but we need to calculate the dew point temperature at 1.5 bar. So how we are going to do it? Tell me. If you remember in the last simulation, I had shown you there are three options that we had for temperature, pressure, and vapor fraction. So out of these three input specifications, what is the value and the specification that we have to choose so that we can get the dew point temperature of this particular mixture? Okay, try to think about it and tell me what we should do over here. Or you can even try to simulate this problem as well. Try to simulate this problem. Take 5 minutes time, try to simulate this problem. Someone had some problem. He wanted to share his screen. Like there was some installation problem. He said that he wanted to share his screen. Is he still there? So what are all the components that we have? We have methane. Next we have ethane. We have propane. We have isobutane. We have butane. We have isopentane. And we have N enter. So this is C1. So what is the property method? RK-Swarm. So you can see all the interaction parameters are updated. Click on next and you're going to run the property analysis. Now coming to the simulation, we are going to add a flash drum. So, flash. This is materials and feed stream and paper stream. What is the input condition? 25 degrees Celsius and 5 bar pressure. 25, 5 bar, and the molar flow rate is 120 kilomole per hour. And the composition is, this is 5%, 105, then we have 0.1%, that is 10% of C2, 15% of C3, 1% of 10% of IC4, 2% of C4, 20% of C4, sorry, 25% of isopentane IC5, and lastly NC5 is 15%. The total is 1. Now we are going to next. Now the question is, what is the definition of dew point temperature? The answer will lie in the definition of this. So if anyone knows the definition, please tell me what is the definition of the dew point temperature.
The temperature at which the entire gas will start the condensation.
Condensation.
Yes.
The temperature at which first drop of that vapor will start form.
So it is also temperature at which the last drop evaporates. Even.
It is the temperature at which relative humidity will reach 100%.
Okay, let us stick with this definition. Relative humidity is going to reach 100%. So that means the mixture becomes saturated
Saturated.
with what? Vapors. Okay. Now tell me what input we have to give. Now that is for a water air mixture, right? The humidity definition that someone just gave right now. Now
Yes, sir.
imagine this to be a mixture of different components, and you have vapor fraction as an input. The pressure is defined. You have to, the pressure is given at what, 1.5 bar, right? So what should be the value of vapor fraction?
Proportion 1.
1. Why 1? Because it is saturated vapor. Yes. So we want the vapor fraction. We want the temperature at which the entire mixture gets converted into vapor. That is the saturated vapors we want. Okay. So we are going to select 1 over here. Now it is saying that the input is complete. Now we are going to click on next. I'm going to run the simulation. So if we go to the blocks, we go to the result. So this is the dew point temperature at this pressure, 1.5 bar. Understood? So for bubble point temperature, what do we have to do?
Put vapor fraction 0.
Yes. For bubble point, we have to put vapor fraction at 0. And just we need to repeat this simulation. So at 1.5 bar pressure, this is the bubble point temperature. Note that the temperatures are very low because these are hydrocarbon mixture. Okay, that is why. They are highly volatile mixtures. That is why these temperatures are so low.
Sir, can we save the result for the
कंपोनेंट वाइज
previous
भी हो
input?
सकता है क्या?
Sorry?
So इसमें कंपोनेंट वाइज भी वी कैन डू कि इस कंपोनेंट तक हमें कंडेंस करना है, इस कंपोनेंट तक नहीं कंडेंस करना.
In that case, you have to like have a good knowledge about the different, uh, what should I say, different boiling point of the different components, and there are separators that are present with which you can have multi side draws. We are going to do it in the coming classes. So over here, these fractionation columns over here, we can derive multiple side draws depending upon the temperature cut that we want.
डन डन ओके सर. एयर से नाइट्रोजन करते हैं ना, एयर से एक्सट्रैक्ट करते हैं, तो उसमें जरूरत पड़ेगा सर.
Okay. So is there any doubt? Fine.
Sir, I had one doubt.
Huh.
Sir, about if we are giving some input, if we want to save it and then change to another input, can we do that? Means both the result at the same time.
No, you can't do that. You can't. It is entirely dependent on the input that you are giving it.
Yes.
So you can't have two inputs for the same simulation and then compare the results. You have to run two different files for that.
Okay, sir.
So is there any doubt? Fine. So this is a very straightforward question. You can try it on your own. So the liquid mixture of
Hello,
60
sir.
mole percent benzene and 40 mole percent toluene is fed with a flow rate of 100 kilomole per hour at 3 bar and 25 degrees Celsius to a flash chamber. It is operated at 1.2 atmosphere and 100 degrees Celsius. So we have to use CSOP 0 method and compute the amount of liquid and vapor products and their compositions. Okay. This question, I had already explained the bubble point question. The dew point, the bubble point is going to be the same as the dew point. So over here, bubble point and dew point both are being asked. So try to simulate this problem and report the answers in the next class. For the bubble point, what you have to do, we have to set it to 0. Sorry, set it to 1 or 0. What do you have to set it to?
0, sir.
Yes.
0.
And so you can do this also on your own. The next problem is
Yes, sir.
that of a is of heat exchange. I don't think we have much time left. So you try to do this problem on your own. I'm going to start with this problem in the next class. Okay. So now I would just like to ask you, is there any doubt that you have in this class or the previous class, or any doubt in the general? This problem I'm going to start in the next class. We don't have much time left now.
Sir, there is one request.
One?
When you upload this video to YouTube, can you please share the link of that Google Drive for the slide you are presenting in that lecture?
You did not get the link as of now?
Maybe I missed. If someone is there, please confirm. Do we get links of the slides sir is presenting?
Yes, you are supposed to get link. Just let me check.
Yes, we get it in the course itself.
Yes, you are supposed to get it in the course.
Like in the problem solving session after
So
this.
whoever is using his or her laptop, just share the screen and show it to everyone else where the link is there.
Sir, like only week one link is showing in
Yes,
the
because
problem
the
solving.
week 2 I'm going to do it today, no?
Okay, sir. I'll show it once.
Yes, just share the screen and show it to everybody. What is the question? Sir, I have to share installation. Okay, yes, you can share. Just give 1 second, let him show how to access the link, and after that you can.
Okay, sir.
This is Aspen Plus, and here in problem solving session, you have to click here, and then there is this week one YouTube link that you can see.
హలో
Okay, got it. Thank you.
వెళ్ళలేదు వెళ్తాను. చిన్న కాల్ ఉంటే మాట్లాడుతున్నాను.
Hello?
మాట్లాడతావా?
Yes, you can share your screen for installation flow.
One minute.